Welcome to the deep dive. Today we're plunging into a topic that sounds like it's been ripped straight from the pages of a mind-bending sci-fi novel. What if reality itself wasn't just observed, but programmed? Imagine a universe built from quantum logic, where even time isn't a fixed arrow, but, a series of astonishing folds and leaps.
Yeah.
It's an idea that fundamentally redefines what it means to build, to simulate, and perhaps maybe even to exist.
It's an audacious vision, to say the least. Our mission today is really to unpack an extraordinary conceptual framework that truly encapsulates this idea. It's officially titled The Time-Jumping and Quantum Tunneling in Virtual Cubic Qubit Systems Blueprint Architecture for Programmable Reality. Quite a mouthful.
Definitely a mouthful.
But this isn't merely about designing faster computers or, better simulations.
Yeah.
It's about defining the very fabric of simulated existence. Think of it as creating a cosmic fast-forward and rewind button for virtual universes, where the traditional arrow of time becomes, manipulable, programmable even.
That's a truly powerful framing. So this blueprint aims to allow designers to completely bypass the physical hardware limitations that plague quantum computing today, right?
Yeah, exactly.
Letting them create quantum software by simulating quantum systems in a perfectly controlled digital space. So you're about to get a unique shortcut to understanding the cutting edge of quantum design, where programmable reality truly means bending the very rules of existence for systems that might one day feel, indistinguishable from our own.
And to guide us, we've sifted through a fascinating stack of sources. We have some pretty in-depth technical papers detailing this ambitious blueprint. We've also got a kind of reality check on the current evolution of quantum AI and some theoretical physics explorations into what time jumps fundamentally mean in the quantum realm. Plus, we'll draw on the foundational criteria for quantum computing, DiVincenzo's criteria, and deep dives into the complexities of many-body systems and quantum circuits. It's a journey from the purely conceptual to the practical hurdles, and then maybe into the deepest theoretical physics that support such a bold vision.
So get ready for some truly mind-bending insights into what the future of computation and maybe even reality itself could look like. Let's unpack this blueprint for a programmable reality. Okay, let's start with the grand promise of quantum computing. We hear about it everywhere, and, for good reason.
Yeah.
It offers extraordinary power, the ability to tackle problems classical computers just can't touch. We're talking about things like complex molecular simulations.
Right, huge potential there.
Which could revolutionize drug discovery, right?
Right.
Letting us perfectly model how a new drug interacts with proteins, or rapidly innovate in material science by simulating quantum behaviors that are currently just beyond our grasp. The potential is immense.
That's the promise, yes. But there's a glaring bottleneck, a huge barrier that prevents us from fully realizing that future. And that's what we call the hardware gap. Current physical quantum hardware is notoriously fragile.
Fragile's putting it mildly, maybe.
Yeah. Imagine trying to build a super-sensitive watch that falls apart if you even breathe on it too hard. It's incredibly noisy, susceptible to even minute environmental disturbances, and highly vulnerable to decoherence.
And decoherence, just to remind everyone, is where those delicate quantum properties like superposition and entanglement, they just vanish.
Precisely. Decoherence is the arch nemesis of quantum computing. Imagine trying to write a message on the surface of a perfectly still pond.
Okay.
Any ripple, any interaction, any environmental vibration instantly distorts and destroys your message. Decoherence is that ripple. It causes qubits to lose their fragile quantum message, their superposition or entanglement, before you can even read it or use it for computation.
Wow.
It's why current devices are often called NISQ, or noisy intermediate scale quantum.
Right, NISQ. Heard that term a lot.
Because they are inherently noisy and limited in their size and complexity, many of the precious few qubits we can create are actually tied up in error correction.
So they're busy fixing errors, not computing.
A lot of the time, yes. Constantly trying to fight off this decoherence rather than performing the actual computation you want. And this severely restricts the circuit depth and complexity you can realistically run.
So it's not just about building them, it's about making them work reliably under incredibly unforgiving conditions. And if the hardware is this unstable, what does that mean for the software?
Well, that instability leads directly to a major software bottleneck. Designing quantum software traditionally demands a deep, often inaccessible understanding of both the abstract quantum principles and the nitty-gritty intricacies of the physical hardware itself.
Okay, so you need to be a physicist and an engineer, basically.
Pretty much. It's like being a brilliant architect who also needs to be an expert in metallurgy, understanding every microscopic flaw in every beam and bolt.
Mm.
This dual requirement is a massive barrier for developers. It slows progress dramatically and makes companies hesitant to invest heavily in quantum software that might quickly become obsolete as the hardware evolves.
Yeah, that makes sense. Why invest if the platform changes tomorrow?
Exactly. Why pour millions into developing for today's quirky, unstable hardware if it might be useless tomorrow when a new, better, but maybe incompatible architecture emerges? This isn't just an inconvenience, it's a fundamental roadblock. It makes quantum software a high-risk, high-reward bet, stifling innovation before it even truly begins.
That sounds like a technological catch-22, a real bind. So if physical hardware is our shaky operating table, where is the steady, sterile surgical suite for quantum software development?
That's where the central innovation comes in. The virtual quantum environment and something called the Virtual Quantic Blueprint, or VQB.
The QB, right.
It's a simulation-first approach, a deliberate strategy to bypass those physical hardware limitations entirely. Designers can create, test, and refine quantum software by simulating qubits in a perfectly controlled, entirely digital space.
Ah, so you build it in the simulation first.
Right. It's like gaining a programmable lens into quantum realities,
Well,
allowing for rapid iteration and experimentation without the physical world's messy constraints.
okay, so a VQB isn't just a static diagram or a file on a computer, right? It's described as a dynamic, living digital map of quantum hardware. How does that actually work in practice? What makes it living?
That's a key distinction. Think of it not as a fixed blueprint you print out, but as a flexible, maybe even self-aware template. It allows for precise, step-by-step manipulation of virtual qubits while simultaneously preserving the integrity of the overall system.
How so?
Well, it maintains its core nature and obeys fundamental quantum rules even as you manipulate its components. It's living because it's interactive, it's responsive, and it enforces the underlying quantum logic. This ensures that even as you shift things around or apply operations, the quantum behavior remains sound and consistent within the simulation.
So it's not just a drawing. It's an active enforcement mechanism for quantum rules within the simulation. That's clever. What are the key building blocks that make up this dynamic map?
Fundamentally, you're working with three core components, which are designed to mirror the actual quantum world as closely as possible. First, there are virtual qubits. These are the digital entities with configurable states. They mirror those fundamental quantum properties like 0, 1, or, crucially, superposition, where they can be both simultaneously.
Okay.
They are the programmable atoms, if you like, of this virtual reality.
The quantum weirdness, but in a digital realm. Got it.
Precisely. Then you have states. These are the mathematical descriptions of those qubit configurations, often represented as vectors in Hilbert space, showing all the possibilities.
Hilbert space, that abstract multidimensional space.
Exactly. Imagine Hilbert space as a vast, multidimensional playground where every conceivable quantum state of a system exists. These state vectors are like coordinates within that playground, precisely pinpointing the qubit's exact quantum condition. And finally, operations. These are your quantum gates, like the Hadamard, which creates superposition, the CNOT, which entangles qubits, or others like Poly-X, Toffoli, Fredkin, and phase shift gates, plus measurements that alter or observe the qubit states. These are the dynamic tools that actually change what's happening within the system, the verbs, if you will.
So it's not just the individual pieces, but also how they relate to each other. How does a VQB define the very being of these virtual qubits and their structural relationships? I'm thinking about ontology and topology here, what they are and how they're connected.
That's a crucial distinction, yeah. Vital for building a coherent virtual reality. Ontology defines the being or inherent nature of virtual qubits. This includes their fundamental quantum properties like superposition and entanglement, and importantly, the meaning or intended function of each qubit within the larger system. It establishes what they are in this digital world, their essence and purpose.
Okay, their fundamental nature. And topology.
Topology, on the other hand, maps their structural relationships, how they connect and interact within a simulated circuit. It defines how they're laid out and linked together, effectively describing their spatial and logical arrangement.
So you can almost imagine the blueprint itself as a dynamic grid-like structure where the cells represent qubits and their states, all interconnected by operations that define the system's topological evolution. It's like a digital scaffolding for quantum computation, but one that constantly updates based on the quantum rules you've established.
That's a perfect analogy. And the VQB is structured to mirror the entire life cycle of a quantum computation through distinct stage-by-stage manipulation, much like a carefully choreographed scientific experiment.
Okay, let's walk through those stages then, because this is where the design process really comes alive. What's stage one? Initialization.
Okay, so here, the blueprint precisely sets the starting conditions for your virtual qubits. This includes defining the total number of qubits you need, their initial states.
Like all zeros, maybe?
Yeah, for instance, setting them all to 0, or immediately putting them into a superposition using a Hadamard gate. And crucially, any early entanglement relationships you want to establish. For example, a blueprint might initialize 3 qubits into a Greenberger-Horn-Zeilinger state, a GH state.
GHZ, okay. That's a specific multi-qubit entanglement.
Exactly. It's a very specific, powerful way to entangle multiple qubits, crucial for many advanced quantum algorithms. This meticulous initialization ensures a consistent, predictable, and reproducible starting point for every simulation run. No ambiguity.
So once the stage is set, the qubits are ready for action. That brings us to stage 2, application of quantum gates.
Precisely. The blueprint then outlines the exact sequence, the type, and the parameters of quantum gates applied to specific qubits, along with their precise timing. These gates are the workhorses. They are what manipulate the qubit states, creating superpositions, entanglement, or phase shifts, all the things critical for any quantum algorithm.
Can you give an example?
Sure. A blueprint might specify applying a Hadamard gate to qubit 1, then a CNOT gate between qubit 1 and qubit 2 to create a Bell state.
A fundamental entangled pair.
Right, a fundamental entangled pair. The blueprint needs to be incredibly precise here, detailing every gate parameter and target qubit for fine control over how the quantum state evolves over time.
And after all those complex manipulations, you eventually need to get results, which leads us to stage 3, measurement.
Indeed. This stage of the blueprint details exactly when and how qubits are measured. This critical act collapses their delicate quantum states into classical bits, either a 0 or a 1.
Bringing them back to the classical world.
Exactly, back to something we can easily read and interpret. It also specifies how these outcomes are recorded and analyzed, often visualized as probability distributions because, quantum measurements are inherently probabilistic.
Right, you don't always get the same answer.
Correct. This step is where the computation is finalized and usable results are extracted from the quantum system. So if you were to measure those entangled qubits we created earlier, you would find their outcomes are perfectly correlated, reflecting their shared quantum history, even though individually their states were uncertain until measured.
Makes sense. And then for even more sophisticated quantum algorithms or complex system designs, there's stage 4, advanced manipulations, right?
Yes, these cover the more complex operations, pushing the boundaries of what's possible. This stage accounts for things like multi-qubit entanglement that goes far beyond simple Bell states.
More complex correlations.
Yes. Or implementing robust error correction codes, which are super important for combating noise in real systems, but also conceptually important in simulations. These codes are sometimes playfully conceptualized within the blueprint as tycoon mode.
Tycoon mode. What's the metaphor there? Why tycoon?
Well, the blueprint's authors playfully call it tycoon mode because it's kind of like a game where you're constantly managing and repairing your quantum enterprise against the decay of noise and errors.
Ah, like a business simulation, but for qubits.
Sort of. You're strategically deploying resources and actions to rectify and protect the delicate quantum information, always building resilience and ensuring the system's continued operation despite environmental challenges, even simulated ones. It could also involve dynamic gate sequences needed for highly sophisticated algorithms that create things like cluster states or implement quantum Fourier transforms, extending the system's capabilities for truly complex problems.
This all sounds incredibly powerful, this virtual approach to quantum design. But what's fascinating here, as you mentioned, is how visualization plays such a critical role. It's not just for us, the human designers, to grasp these incredibly abstract concepts, but apparently for the virtual systems themselves to understand what's happening.
Absolutely. Visualization transforms these abstract concepts into tangible interactive models, making the invisible visible. It's essential given the inherent complexity of quantum mechanics and the, current limitations of physical quantum hardware. For a single qubit, the Bloch sphere is fundamental.
Ah, yes, the Bloch sphere.
It's a three-dimensional visual representation that clearly pictures its state, its superposition, and its phase. It allows you to intuitively see its quantum orientation.
Okay, and for multiple qubits.
For notable qubits, circuit diagrams are essential for showing the computation flow and providing a topological view of their operations, much like traditional schematics, but, adapted for quantum processes.
So more like traditional schematics in a sense, but for quantum processes. And I imagine interactive simulators are an absolute must-have for developers. Like, you need to be able to play with it.
Oh, definitely. Interactive real-time simulators are the workbench for designers. They allow you to immediately tweak parameters, change gates, or adjust qubit states and observe the effects in real time.
Instant feedback.
Exactly. Providing crucial feedback and rapidly building intuition. They often leverage things called virtual quantum processors, or VQPUs, for that rapid iteration, letting you truly experiment with quantum logic without ever touching physical hardware. Kick the tires, so to speak.
And what about those amazing, almost artistic concepts we touched on earlier, like crystallographic glyphs and topology-preserving morphs? How do they visualize those deeper, more abstract system properties?
This is where the visualization gets truly innovative, maybe even a bit esoteric. Crystallographic glyphs transform abstract mathematical symmetries, like those defining crystal structures or fundamental quantum operations, into tangible, often beautiful visual shapes.
So you're literally seeing the symmetry of quantum logic.
In a sense, yes. And topology-preserving morphs are advanced animations that smoothly morph underlying structures and glyphs while ensuring their connections remain intact. This allows for a dynamic visual tracking of the system's evolution over time. So you can watch how the structure changes, but always remains coherent and understandable. The relationships persist visually.
Oh, that's incredibly cool. And in entanglement, how do you visualize something that's so inherently non-local and correlated across a system? That seems really hard to draw.
Yeah, it is. Entanglement is often visualized as glowing, persistent links, forming a dynamic 3D graph between qubits. These links represent those abstract, non-local connections, making them visible as if glowing threads connect the entangled particles.
Oh, okay, like threads of connection.
And for quantum error correction, or our Tycoon mode, it's sometimes presented as a 3D lattice, with color-coded error anomalies that are actively corrected by stabilizer agents within the simulation. Here, you're visually representing decoherence as a kind of dynamic fog or corruption that Tycoon mode actively pushes back and clears, showing the system's resilience in real time.
That's a powerful visual metaphor for fighting noise. What about the symbolic interactions we heard about earlier, like the manipulations field of letters components? Sounds intriguing.
That's an interactive layer, where users can directly manipulate symbolic representations like Q1 for qubit 1H for Hadamard, or even those Hebrew glyphs discussed in the blueprint's deeper mathematical underpinnings.
The Kabbalistic connection again.
Right. And you observe their immediate effects on underlying quantum states and visualizations within a virtual grid. These symbolic changes directly reflect the topological structure and quantum logic. Even subtle parameters like flux control changes in superconducting qubits can be modeled as 3D wave distortions around a qubit, giving designers an intuitive feel for how those physical parameters affect quantum states.
What's the underlying technology that brings all these complex visuals to life, making this programmable reality so interactive? Is it specialized stuff?
Actually, a lot of it relies on web technologies. Three.js, a powerful JavaScript library, is integral for rendering abstract quantum concepts and manipulations into tangible, interactive 3D models within a web browser.
Wow, JavaScript for quantum design.
Yeah. So web technology is powering quantum design, used for everything from the Bloch spheres to visualizing entanglement and error correction. And importantly, the QLOS Degree 4 user interface mentioned in the blueprint is itself conceived as a comprehensive 3D visualization space, displaying all those real-time data overlays to give designers immediate rich feedback. This truly shows the depth of a programmable reality, making the abstract actionable.
Okay, what's truly fascinating here is how the virtual quantic blueprint we just explored really paves the way for something even more audacious, the JUMPS blueprint. This is a vision that extends far beyond mere computation, hinting at a reality that can be truly sculpted and edited, almost playing God with the simulated universe.
Indeed. The formal title alone captures its extraordinary scope. Time jumping and quantum tunneling in virtual cubic qubit systems blueprint architecture for programmable reality. Its goal isn't just about achieving computational speed or simulating complex systems. It's about defining the very fabric of simulated existence. Imagine, as we touched on earlier, that cosmic fast-forward and rewind button for virtual universes, where the traditional arrow of time becomes a manipulable, programmable dimension.
Yeah.
This isn't just simulating a universe. It's defining the very rules by which it operates, including its temporal evolution, how time itself behaves.
Wow. Okay, so what are the 5 foundational design concepts that drive this kind of programmable reality, these core pillars that allow for such profound manipulation?
At its heart, the blueprint defines 5 key design concepts that form the very fabric of this proposed reality. First, time jumping.
The big one.
The big one. They model this as nonlinear, discrete, instantaneous transitions between quantum states across what they call time-folded layers. This isn't a smooth progression, but a sudden, discrete leap, akin to skipping moments or even whole periods of a quantum system's evolution.
Like editing a movie, cutting scenes.
Sort of, yeah. It's like flipping a switch to jump to a new state, rather than slowly turning a dimmer dial. Instantaneous change.
So jumping, not flowing. A sudden, non-linear shift. What's the second concept?
Second, quantum tunneling. Now, this is simulated as logic state transitions between encapsulated qubit systems. Crucially, this happens without needing classical connections.
No wires needed.
Essentially, yes. In this simulated reality, it's as if information just appears on the other side, a direct logic state transfer that bypasses conventional physical travel or signaling. It's like a secret shortcut built into the very logic of the universe.
That's mind-bending. Information just popping into existence on the other side, seemingly defying distance within the simulation.
Precisely. Third, and this is central to the blueprint's foundation, is virtual qubit blueprinting. This is the initial design of those qubit logic units, not as abstract points, but as intricate 3D cubes embedded with material and ontological data.
Okay, what does that mean, material and ontological data?
What this means is that each virtual qubit isn't just a theoretical component. It's designed with built-in information about its virtual composition, its inherent meaning, and its function within the larger system. Think of it like designing the perfect Lego brick for reality, where each brick already knows exactly what it is, what it's made of in the virtual sense, and how it's supposed to behave and contribute to the grander structure. It's purpose-built from the ground up.
That's a great analogy. It really emphasizes the built-in purpose and structure.
Very cool. What about the fourth concept? Fourth, we have self-configuring systems. This concept envisions recursive logic architectures designed to evolve and optimize themselves. These systems are not static. They learn and improve their own structure using internal quantum feedback, constantly reshaping and refining themselves based on their performance and goals.
So an AI that could literally re-engineer itself, not just its code, but its very foundational structure, its own building blocks.
Potentially, yes. And the last one.
Fifth is ontological topological maps. These are essentially 3D or even 4D maps that encode meaning, structure, and transformation logic for everything in the system.
They act like a comprehensive, self-updating operating manual for the entire virtual universe, defining how everything relates, interacts, and changes within this simulated reality.
Yeah.
They're the master plan and the dynamic rulebook rolled into one.
That's a lot to wrap your head around. It really sounds like they're thinking about every single layer, from the fundamentals right up to how the whole system evolves and manages itself. Can you give us a glimpse into some of those specific design layers and the software infrastructure that make this blueprint a tangible framework?
Absolutely. The full system design is incredibly comprehensive, detailing not just concepts, but how they'd be implemented. For instance, in virtual qubit architecture, they're not just talking abstract qubits. They're designing them as intricate 3D cubes with specific structural anchor nodes.
Anchor node.
Yeah, almost like defining the exact joints and hinges for these quantum building blocks. This level of detail allows for precise control over their internal properties and how they connect.
Very detailed. And it goes into virtual material science, too.
Yeah.
Simulating materials.
Yes. There's the material science and virtual matter modeling layer. This gets into mapping these qubit designs to actual known 2D quantum materials, like graphene, and simulating programmable metasurfaces. They even aim to predict how these virtual designs would act if they were physical, going as far as predicting quantum phase changes, like a material suddenly becoming a superconductor, all within the simulation. This allows for rapid prototyping of novel materials virtually.
And the software itself is evolving? You mentioned that? That sounds like a meta level of programming.
Indeed. They detail the software infrastructure, which includes developing entirely new self-evolving blueprint languages like Higyan-Lang and QLOS, the Quantum Linguistic Operating System.
QLOS.
These aren't just programming languages in the traditional sense. They're designed with recursive logic to write and rewrite their own quantum rules, allowing the languages themselves to evolve their own code and capabilities.
Languages that rewrite themselves.
Wow. Yeah. QLOS, as a meta-framework, applies the blueprint concept to the entire programmable material of any system, meaning it can understand and modify the very foundational elements of the simulated reality. It can even suggest changes to the virtual quantum blueprint based on AI-driven insights, essentially self-optimizing the fundamental rules of the simulated universe.
Languages that evolve their own code and an AI that can reshape the blueprint of a reality. That's truly amazing. If this blueprint were to actually materialize, what are the most audacious applications? What could this programmable reality really achieve?
The blueprint outlines several, frankly, mind-bending use cases, pushing the boundaries of what we currently imagine technology can do. First, imagine self-designing AI architectures.
We touched on that.
Yeah. This isn't just AI that writes better code. It's AI that could literally re-engineer its own fundamental structure, evolving its own cognitive processes and capabilities beyond any human-programmed limits. We might see intelligence emerge in ways we can't currently predict.
That sounds like a true leap in artificial intelligence, a different kind of AI altogether. What else?
Then there are time-fold quantum communication systems. This proposes communication that could potentially bypass linear time for instantaneous information transfer by leveraging these simulated time jumps.
Instantaneous communication across any distance.
Within the simulation, potentially, yes. Imagine not being constrained by the speed of light for communication across vast cosmic distances within this virtual reality. Information could be effectively tunneled across space-time, profoundly changing how we conceive of data transmission and even interstellar exploration within these simulated worlds.
Wow. Instantaneous communication sounds revolutionary, even simulated. What else?
They also list quantum material blueprint simulators, which would allow for rapid innovation in material science through virtual simulation. Designers could test millions of hypothetical quantum materials in a fraction of the time it would take to synthesize them physically.
Speeding up discovery.
Massively, leading to breakthroughs in fields from energy to electronics. There are also virtual reality physics engines designed to create truly realistic VR experiences where the physics is entirely self-consistent based on these quantum rules. This would mean VR environments so profoundly real that they could potentially become indistinguishable from physical reality in terms of their physical laws. True programmable physics.
And what's the final, most audacious application listed?
Finally, transdimensional data transmission simulation models. This concept aims to revolutionize how information is accessed and moved, potentially allowing data transfer and retrieval far beyond our current physical limits within the simulation. It hints at entirely new paradigms for accessing information across vast, seemingly disconnected datasets, perhaps even suggesting forms of data retrieval that feel, well, transdimensional, whatever that means in this context.
So this isn't just some abstract thought experiment. This blueprint is the foundational thinking behind possibilities that could fundamentally change everything. How we interact with technology, information, and maybe even our very understanding of reality itself. It truly embodies the idea of a cosmic fast-forward and rewind button for virtual universes.
That's the grand vision, yeah, a complete redefinition of what it means to create a system. Now, you might be wondering, and I certainly am,
Yeah.
how does this audacious blueprint align with our current understanding of physics, especially regarding time jumps? Is this something that's actively being built today, or is it purely conceptual, just a theoretical dream for now?
That's an excellent and crucial question, and it brings us neatly to the reality of time jumps, how physics and this blueprint intersect. In classical physics, time is just an external parameter, right? A universal clock ticking outside the system, which seems straightforward enough. But in quantum mechanics, it's potentially far more complex and active.
Indeed. In quantum mechanics, time can be described as an operator itself, meaning it's not just a passive background, but an active, measurable quantity. It's intimately connected to the energy operator, or Hamiltonian, which describes the total energy of a quantum system. This connection leads to an energy-time uncertainty principle.
Ah, like the position momentum one.
Exactly like that, yeah. Similar idea. It means there's an inherent trade-off, a fundamental blurriness. The more precisely you try to measure how long a quantum event takes, the less certain you become about its energy, and vice versa. You can't know both perfectly at once. This already suggests a more fluid, less absolute concept of time at the quantum level.
So even standard quantum mechanics has a fuzzier, more active concept of time. But then there's this other idea, the one that really challenges our intuition, time moving forwards and backwards. That sounds wild.
Ah, yes. That's where Yakir Aharonov's two-state vector formalism, or TSVF, comes in. It's a different, pretty intriguing way of looking at quantum states, proposed to better describe certain quantum phenomena. It describes a quantum system not with just one state evolving forward from the past, which is called pre-selection,
The normal way.
the normal way, but also with another state evolving backward from a future measurement outcome, which is called post-selection.
Whoa, backwards in time. That sounds paradoxical. How does that even work?
It really is mind-bending. But this formalism allows for a backward influence in time, where future states can modulate past states without introducing classical paradoxes.
How? How does it avoid paradoxes?
Because this influence remains hidden or potential until the final measurement crystallizes the entire history. Think of it like a choose-your-own-adventure book, where the ending you pick can subtly change the meaning or even the specific events of earlier chapters, even though those chapters were written first.
Okay. The ending reframes the beginning.
Exactly. The Phoenix Time Simulator, a concept specifically mentioned within this blueprint framework, specifically models these retrocausal updates where future states effectively nudge past events without violating causality in a way that creates grandfather paradoxes or things like that. It's subtle.
So with that kind of framework in mind, what do these time jumps actually mean phenomenologically at the quantum level? We're definitely not talking about a DeLorean hopping through centuries.
Right? No, definitely not a time machine in the sci-fi sense of physically traveling to a different historical period. When physicists talk about time jumps phenomenologically in quantum systems, they mean discrete instantaneous transitions rather than smooth linear changes.
Like flipping a switch?
Exactly. It's akin to flipping a light switch from off to on, not slowly turning a dimmer dial. There's no in-between state, just a jump. A classic example is the collapse of the wave function. If you perform a precise time measurement on a quantum system, the system might jump to a specific time value for that measurement outcome. The precise moment of this collapse itself is discretely sampled, not a smooth, continuous evolution.
So the very act of measurement can cause the system to jump in time or state.
Yes, the active measurement, especially projective measurements of the time operator, can force these instantaneous transitions. This also connects to some other fascinating quantum effects, like the quantum Zeno effect.
The watched pot never boils effect.
Pretty much. If you measure a quantum system frequently enough, you can essentially freeze its evolution, preventing it from changing or decaying. Conversely, there's the anti-Zeno effect, where, under certain conditions, frequent measurements can actually increase the probability of the system transitioning between states, making it jump more often. Experiments with trapped ions, for instance, have actually demonstrated this kind of hopping between energy levels, influenced by how they're measured or interacted with.
So we can potentially freeze a quantum state or speed up its changes just by observing it in the right way. That's truly mind-boggling and challenges our classical intuition for sure.
It absolutely does. And what's fascinating here is how this idea of jumping extends beyond just single energy levels or states. It can apply to more complex scenarios. You can think of a larger quantum system as a kind of supersystem made up of several smaller subsystems. Each of these smaller parts lives in its own sort of quantum space, its own Hilbert space.
Okay.
Jumping between these subsystems is a complex phenomenon involving interactions that essentially connect these different spaces. For example, if you measure something in subsystem B, subsystem A, even if it's spatially separate, can instantaneously switch to a new state or configuration due to their entanglement.
Spooky action at a distance.
That's the one. This is called a modular jump, creating what's described as a non-local time image, which implies instantaneous information transfer between entangled, spatially separated subsystems.
So what are the actual physical mechanisms that are understood to cause these quantum jumps? What makes them happen?
The sources highlight a few key mechanisms. First, a quantum quench. That's a sudden, abrupt change in the system's parameters, like its energy settings, what we call the Hamiltonian.
Like giving it a sudden jolt.
Exactly. Imagine suddenly changing the magnetic field around a qubit. That abrupt shock can force a discrete jump in the state.
A sudden, forceful push to the system.
Exactly. Second, measurement-induced jumps. As we discussed, projective measurements, especially if you could precisely measure the time operator, can cause the system to jump from an initial moment, say t0, to a specific outcome, tn, without passing through the moments in between. The very act of looking forces the leap, in a sense. And third, transitions between quantum system types. This could be a fundamental quantum phase change, like a material suddenly becoming a superconductor or a superfluid, an immediate discrete shift in its collective quantum properties. Or it could be the immediate jump of an entangled subsystem upon measuring its partner, that demonstration of quantum non-locality.
Okay, so we've got this really profound, if mind-bending, theoretical understanding of quantum jumps. These instantaneous shifts in time and state, supported by intriguing physics. Now, bringing it all back to our central topic, how might these abstract phenomena actually be engineered into that ambitious, programmable reality blueprint we started with? How do you even design for something as complex as a time jump in a simulated universe?
That's where the blueprint's program design becomes incredibly sophisticated. It includes a layered control and orchestration system. At the top, there's a scenario manager, a blueprint compiler, and crucially, a dedicated time jumpular.
A jumpular, seriously.
Yeah, that's the term they use. It's essentially a sophisticated scheduler specifically designed to orchestrate and manage time jumps within the simulated reality. All that feeds down into the core simulation engine. Inside that engine, specific modules are designed to handle these quantum time concepts. There's the VCQ model, which stands for Virtual Cubic Qubit, and its job is to create and manage the virtual qubit objects based on the intricate blueprint files.
Okay.
Then there's a gate engine, which applies the standard quantum operations, but it also specifically schedules those quench events. We talked about the sudden Hamiltonian changes that could trigger jumps within the simulation.
So actively programming, the equivalent of a sudden shock to the system, that's a level of control beyond anything we usually think of in computation, really designing the dynamics.
Yes, it's about engineering the very dynamics of the simulated reality. And then there's the tunnel module. This acts as the time jump controller. It receives the time jump instructions from the jumpular, checks if they're feasible within the simulation's rules, and then performs the virtual state transfer.
How does it do the transfer?
According to the blueprint, this could happen in two main ways. Either by state reinitialization in a target timeline, basically hitting a virtual reset button and starting fresh in a new simulated moment with a new history.
Like loading a save game, almost.
Kind of. Or by branching into a parallel VQB instance, creating a whole separate simulated reality, but one that shares an entanglement history with the original, effectively creating parallel timelines within the simulation.
Wow, it's incredibly complex and multi-layered. It's not just about what to simulate, but how to simulate the very fabric of time and causality within it.
It's a truly intricate system design, demonstrating how they're attempting to meticulously plan for incorporating these deep theoretical quantum ideas into something functional, at least in simulation. It's a testament to the ambition of the JUMPS blueprint.
Now let's zoom out a bit and talk about the fundamental requirements for any quantum computer, whether it's a physical device or a virtual simulation. This brings us to DiVincenzo's criteria, often considered the to-do list for building a practical quantum computer. These are 7 rigorous conditions proposed by David P. DiVincenzo back in 1996, and they highlight both the complications arising in dealing with quantum systems and, paradoxically, the very source of quantum power.
That's right. These criteria are critical because they define what a quantum computer must be capable of to truly harness quantum mechanics for computation and communication. 5 of these conditions are necessary for quantum computation itself, and 2 additional ones are for quantum communication. The virtual quantic blueprint we've been discussing aims to fulfill these requirements in a simulated environment, often sidestepping the immense physical challenges.
Okay, let's unpack the 5 for computation. Number 1, a scalable physical system with well-characterized qubits. What does well-characterized mean, and why is scalability such a hurdle in practice?
Well-characterized means each qubit must be precisely identifiable and controllable, with predictable behavior. You know what it is and how it acts. The challenge here is creating a system with an arbitrary number of these perfect qubits without needing exponentially larger or more complex setups for each additional qubit.
It gets harder as you add more.
Exactly. For instance, early liquid-state nuclear magnetic resonance, or NMR, quantum computing struggled with this. As they tried to increase the macroscopic size of the samples, the qubits became highly mixed states, meaning their quantum signals became too weak to be useful without increasing the sample size even further, which is simply not scalable. The key insight for the VQB here is that in a virtual environment, you can define an arbitrary number of perfectly characterized virtual qubits, sidestepping this monumental physical limitation entirely. You just add more in the code.
So it's about quality and quantity that doesn't balloon out of control. Number 2, the ability to initialize the state of the qubits to a simple fiducial state. Why is initialization so crucial? Setting the starting point.
It's fundamental for all quantum computation, and especially for quantum error correction. Many quantum processes are robust against noise, but they critically depend on having a large supply of freshly initialized qubits, placed in a known pure starting state, typically all zeros. This places strict restrictions on how fast this initialization can be. Often, in physical systems, this is accomplished by letting the system cool down or anneal to its ground state.
Letting it settle down naturally.
Right. However, the speed is critical. Preparing a bell pair of electrons in quantum dots, for example, can take milliseconds, which can be a roadblock if decoherence times are shorter than the initialization time. You lose the state before you even start properly.
Uh-oh.
Alternative approaches like optical pumping have been developed to reduce this time and improve fidelity. In the VQB, initialization is trivial. You simply program the desired starting state, offering perfect instantaneous control. Solved.
And then there's the big one related to the noise we discussed earlier. Number 3, long, relevant quantum coherence times, keeping the quantumness alive.
Decoherence, as we established, is indeed the nemesis of quantum computing. The quantum resources, superposition, and entanglement are quickly destroyed by unwanted environmental interactions. For a quantum computer to be practical, we need coherence times to be much longer than the average time it takes to perform a quantum gate operation.
Why much longer?
So that decoherence can be combated with error correction or dynamical decoupling techniques, which themselves take time and require multiple gate operations. What's fascinating and frustrating is that systems that can be manipulated quickly through strong interactions often experience decoherence via these very same strong interactions.
The thing that lets you control it also messes it up.
Exactly. So there's a fundamental trade-off between the ability to implement rapid control and increase decoherence. The VQB, by existing in a perfectly isolated digital realm, inherently has infinite coherence time, removing this major physical constraint and allowing designers to focus purely on quantum logic.
It's like a double-edged sword in the physical world. Number 4, a universal set of quantum gates, being able to do any computation.
In both classical and quantum computing, the algorithms we can compute are restricted by the set of basic operations, or gates, we can implement. For a quantum computer to be universal, meaning it can perform any quantum computation, you need a small set of 1 and 2 qubit gates that can approximate any operation. The experimental setup must be capable of coherently influencing the system's Hamiltonian, or total energy, to implement these gates. Liquid-state NMR was one of the first systems to achieve this, but as we mentioned, it wasn't scalable. The VQB offers direct, perfect implementation of a universal gate set, as each gate is simply a mathematical operation defined in the software. No problem there.
And finally, for computation, number 5, a qubit-specific measurement capability, getting the answer out reliably.
This is absolutely fundamental. For any process-modifying quantum states, the final measurement is of paramount importance for performing computations and extracting results. If your system allows for non-destructive projective measurements where you measure a qubit without altering it, if it's already in an eigenstate, that's ideal, though not always possible. Measurement is at the foundation of all quantum algorithms, even concepts like quantum teleportation. Examples of reliable measurement are found in optical systems with homodyne detectors, but measuring the state of quantum dots, for instance, is far more challenging. In the VQB, measurement is again perfectly controlled and non-destructive in its simulated form, offering idealized outcomes crucial for complex algorithm development.
Okay, so that's the 5 for computation. Then there are 2 more for quantum communication. Number 1 of those, condition 6, the ability to interconvert stationary and flying qubits. Stationary and flying.
Yeah.
Right.
This is crucial for protocols like quantum key distribution, which involve the exchange of coherent quantum states or entangled qubits over distances. When you create entangled qubits in the lab, they're often stationary trapped ions or superconducting circuits, for example. They stay put.
Okay.
The ability to convert them into flying qubits, such as encoding their quantum information into the polarization of a photon, allows for their transmission over distances. This enables things like distributing entanglement to a third party or building quantum networks.
Sending the quantum info on the move.
Exactly. The VQB, by its nature, can model this interconversion perfectly within its simulated environment.
And the final condition, number 7, the ability to faithfully transmit flying qubits between specified locations, sending them without losing the message.
Decoherence during transmission is a major problem for any physical quantum communication. For example, at the Institute for Quantum Computing, there are efforts to produce entangled photons and transmit one by reflecting it off a satellite.
Bouncing photons off satellites. Wow.
Yeah. The main issue is the decoherence the photon experiences interacting with particles in the atmosphere. Similarly, while optical fibers have been attempted, signal attenuation and loss of quantum coherence have prevented widespread practical use over long distances so far. These criteria really underscore the monumental engineering challenge of building physical quantum computers and communication networks, which is precisely why the virtual approach of the JUMPS blueprint is so vital. It bypasses these physical hurdles to develop quantum logic unhindered.
This brings us to a really important question. Why are quantum computers needed in the first place? We mentioned simulations, but the deep reason often comes back to the many-body problem. What exactly is that, and why is it so intractable for classical computers?
The many-body problem is a general name for a vast category of physical problems pertaining to the properties of microscopic systems made of many interacting particles. Many here can be anywhere from just 3 particles to, well, effectively an infinite number. It applies to any scenario where quantum mechanics is needed for an accurate description, which is essentially all of chemistry and material science.
So even 3 particles interacting quantum mechanically can be many enough to cause a huge problem for calculations.
Precisely. While the underlying physical laws governing individual particle motion might be simple, studying a collection of particles rapidly becomes extremely complex. This is due to the intricate quantum correlations and entanglement that emerge. In such a quantum system, the repeated interactions between particles create this complex web of interdependence. As a consequence, the system's overall wave function, which describes all possible states simultaneously, well, it becomes an incredibly complicated object holding an exponential amount of information.
Exponential again, that word keeps coming up.
It's the key. This makes exact or analytical calculations impractical or even impossible for classical computers.
And I understand that complexity scales exponentially, right? This is the core reason classical computers struggle so badly.
Exactly. In classical mechanics, describing n particles scales linearly. If you double the particles, you roughly double the computational effort. Simple enough. But in quantum mechanics, it scales exponentially with n. This is because, due to superposition and entanglement, you must account for all possible combinations of single-particle states simultaneously. The required numerical expense for classical computers grows so quickly, ridiculously quickly, that simulating the dynamics of more than a handful, say, 3 or 4 quantum mechanical particles, is already infeasible for many physically relevant systems on even the most powerful supercomputers today. This exponential scaling is why quantum computers are uniquely envisioned as the solution to efficiently tackle this many-body problem and unlock breakthroughs in fields like drug design and material science. They speak the same quantum language.
So few-body systems are just a subset of that, where the particle count is small but still intractable for classical approaches, right? Just a few is enough to break classical methods.
Yes. Few-body systems are typically defined as consisting of a small, manageable number of well-defined structures or point particles, usually in between simple 2-body systems and truly large and many-body systems. Examples include light nuclear systems, small molecules, or quantum dots. The challenge here is still immense. The Schrödinger equation, the fundamental equation of quantum mechanics, is not analytically solvable for more than 2 mutually interacting particles, even just 3 bodies.
Can't solve it exactly.
Right. This is often referred to as the few-body problem within this context, requiring iterative or complex numerical solutions, like the Fedde equations, even for a small number of particles. Still very hard classically.
This all hinges on understanding the fundamental building blocks, point particles. Classically, they're an idealization, right? 0 size. But in the quantum realm, it gets incredibly nuanced.
Indeed. Classically, a point particle is a convenient idealization, a mass or a charge, concentrated at a single dimensionless point. It's useful when size, shape, and internal structure are irrelevant, like modeling planets as point masses for gravitational calculations. Simple. However, in quantum mechanics, the concept is complicated by Heisenberg's uncertainty principle. An elementary particle, even one without internal structure, cannot be precisely localized to a single point. It occupies a non-zero volume due to its wave-like nature.
Ah, the wave-particle duality.
Exactly. Think of the atomic orbital of an electron. It's not a tiny ball orbiting the nucleus, but a probability cloud occupying a region of space. It's spread out.
So an electron isn't really a point in the classical sense, even though it has no internal parts we know of.
Not spatially localized to a single geometric point, that's correct. We
Oh.
make a distinction. Elementary particles, like electrons, quarks, or photons, have no known internal structure. They are considered point particles. In that sense, their internal size or structure is considered precisely zero, even if their wave packet is non-local and spread out in space.
Okay. And composite particles.
And then there are composite particles, like protons and neutrons, which do have internal structure being made of quarks. Now, the JUMPS blueprint's design of intricate 3D cubes for virtual qubits to literally contrast with this idealized point particle concept.
How so?
It emphasizes that these virtual qubits are not just abstract points in computation. They have a built-in structural and ontological data, a predefined composition, internal meaning, and a specific function within the simulated reality. They are literally the designed building blocks of a new programmable existence, not just fuzzy quantum points.
Okay, let's dive into some of the truly mind-bending architectural mathematics that underpins this JUMPS blueprint. This is where the framework moves beyond conventional physics and computer science, seeking to unify disparate fields to create a universal language for programmable reality. This is the master framework, unifying Kabbalah and crystallography. Sounds ambitious.
It's incredibly ambitious. What's truly revolutionary here is that the blueprint's creators sought a truly universal language for designing reality. They looked beyond conventional physics to ancient systems that also sought to map fundamental patterns of existence. They propose a deeply ambitious 40-chapter structure that consciously weaves together ancient Kabbalistic letter cosmology, specifically drawing from the Sefer Yetzirah's 231 gates, which are derived from the 22 Hebrew letters.
Okay, the mystical tradition.
With modern crystallography, drawing on its precisely defined 230 crystallographic space groups. This framework integrates data artifacts, visualizations, advanced AI models, and futuristic extensions. The goal is a structural, computational, and geometric understanding. It aims to move beyond any mystical framing, to focus on how these abstract forms represent fundamental cognitive constraint and possibility for any reality, physical or simulated.
So using ancient patterns as a guide for computational structure.
Kind of, yeah. It's about finding the universal grammar of existence, wherever that grammar might be found.
That's a fascinating, almost philosophical ambition for a technical blueprint. And within this master framework, there are these 36 unity points, projective encoding units. Where do these precise numbers come from mathematically, and what do they represent in this system?
They derive from a simple, but maybe profound 6x6 combinatorial system. Imagine the 6 faces of a cube. If each face can contain 6 distinct points or operations, multiplying them gives you 6 by 6 equals 36 unity points.
Okay, 6 by 6. Simple enough.
But these aren't just arbitrary points. They are conceptual projective reflections that describe how each face encodes the orientation and transformations of the entire 3D structure. Their function is to encode a partial isometry or transformation, like projective reflections or rotations, mapping across the cube's 3D lattice. You can think of them as the fundamental programmable verbs or actions within the system. They are actualized encoding units, local and deterministic, acting as precise rights or commands that shape the system's space.
Okay, the actions. That brings us to another fascinating precise number, the 126 obstruction boundary, a combinatorial ceiling. This sounds like a hard limit, a kind of maximum capacity for coherence or complexity.
It is, in a way, a defining constraint for this simulated reality. Mathematically, it comes from considering a set S of 9 orthogonal directions. Think of these as the 3 Cartesian axes, x, y, z, plus the 6 body diagonals within a cube, giving you 9 fundamental orientations.
9 directions in a cube. Got it.
The number of non-empty subsets of these 9 directions, with a size of up to 7, sums up to 126. This is calculated by the sum of binomial coefficients, of k 1 to 7, C9k 126.
So it's a very specific combinatorial outcome based on those 9 directions. But what does this 126 truly mean in the context of designing a programmable reality? What's its function?
This 126 is interpreted as a combinatorial threshold, or a symbolic obstruction boundary. It represents the total number of structurally meaningful subspaces or configurations that can be generated from selecting up to 7 of these 9 fundamental directions simultaneously. It functions as a constraint envelope or a set of permitted configurations, defining the limit of constructive combinatorial complexity without full closure.
Limit of complexity. Okay.
The blueprint suggests that beyond this 126 threshold, emergence breaks down, interference occurs, or coherence gets lost. This isn't just abstract math, it's literally designing the guardrails of a simulated reality. It acts as an epistemic membrane within which the symbolic language AI crystallizes, reflects, and acts, serving as the safe horizon of coherence. It ensures that the symbolic grammar of the virtual universe remains consistent and doesn't devolve into contradiction or chaos.
So a hard boundary for stability and meaning within the simulation, that's a truly powerful idea for a simulated reality, defining its very limits of consistent existence. What about the duality and algorithmic interpretation between these 36 points and the 126 boundary? How do they play off each other?
They represent a fascinating duality. Geometrically, the 36 unity points live in a projective 3D framework, governing specific transformations like cube faces or rotational symmetries, actions on the surfaces. The 126 boundary, however, lives in a more abstract combinatorial 9D space, defining the potential orientations or combined states that cannot fully stabilize if too many directions are combined without closure. Limits on combinations.
Okay.
Algorithmically, the 36 unity points are low-bound, deterministic, and local projections, acting as actualized encoding units or direct writes into the system space precise commands. In contrast, the 126 are upper-bound, probabilistic configuration limits, acting as overarching rules for preventing overflow or contradiction in high-dimensional symmetry. They complement each other by providing both the specific actions and the overarching limits.
The actions and the rules. And how do these numbers, these dualities, tie into crystallographic and symbolic relevance, effectively bridging ancient cosmology with modern structural science? How does it all fit?
This entire framework forms a comprehensive grid of symmetry encoding. It spans symbolic algebra, represented by the 231 alphabetic pairings from Sefer Yetzirah's letter cosmology. It incorporates lattice geometry, drawing from the 230 precise crystallographic space groups and their symmetry operations. Then it integrates structural topology through the 36 unity points, and finally constraint theory via the 126 subset boundary.
Bringing it all together.
Right. In a cube-based projection model, the unity points serve as the nodes, the fundamental points of action. The 126 subsets define the legal transformation states, the permissible configurations. The 230 groups provide the action rules, how things can change. And the 231 pairs serve as the labeling system, the language to describe it all. It's a complete, integrated system for defining the fundamental structure, logic, and limitations of a virtual universe, drawing from maths, physics, computation, and even ancient symbolism.
This is truly extraordinary in its ambition, seeking to find universal patterns across such disparate domains to inform the design of reality. But let's ground this a bit. How are these ambitious principles, or at least similar concepts of quantum control and simulation, translating into practical acceleration of quantum simulations today? How do we actually speed things up now?
That's a crucial leap from the abstract to the immediate. The challenge, as we discussed, is immense. Simulating quantum circuits is computationally intensive. It faces that exponential growth in data storage and execution time as the number of qubits increases. Even a few dozen qubits can push the limits of classical supercomputers to their breaking point.
So what specific techniques are being used right now to speed this up, to make these complex simulations feasible on current hardware?
There's a lot of active research across different hardware platforms. For CPU-based techniques, which are still widely used, people are working on sophisticated state vector compression.
Shrinking the data.
Yeah, which can be lossy or lossless to reduce memory footprint. They're optimizing data formats, for example, using 32-bit floats instead of 64-bit doubles to have the memory needed if precision loss is acceptable for the specific problem. Other methods include circuit partitioning, breaking large circuits into smaller, manageable chunks, gate clustering, and parallel execution across many CPU cores to distribute the workload. Divide and conquer.
And what about leveraging specialized hardware like GPUs or FPGAs? They're used a lot in AI, right?
Absolutely. GPU-based simulations are incredibly powerful. They leverage the massive parallelism of graphics processing units, which are excellent for the massive matrix multiplications and linear algebra inherent in quantum simulation.
Perfect match.
Pretty much. These approaches involve tailored acceleration strategies and often specialized libraries like Quantum that efficiently map quantum operations to GPU architectures. Beyond that, FPGA-based approaches, using field-programmable gate arrays, offer unparalleled flexibility.
FPGAs. Those reconfigurable chips.
Yes, exactly. FPGAs allow for custom hardware architectures that can be reconfigured for specific tasks. They excel with limited resources, using techniques like precomputation and stream-based complex, multiply and accumulate CMA operations. It's been discovered that with careful hardware design on FPGAs, it's possible to achieve an astonishing O(n) time complexity, where n denotes the number of qubits, in stark contrast to a standard Python NumPy implementation, which might be O2N runtime.
Wow, linear scaling versus double exponential. That's insane.
It underscores the incredible feasibility and importance of custom hardware acceleration for quantum simulations. It shows it can be done efficiently.
It's really fascinating how the huge developments in the machine learning domain, with their intense need for fast matrix operations, are synergistically benefiting quantum simulation, allowing for such dramatic speedups.
Absolutely. There's a lot of cross-pollination of techniques.
Yeah.
This brings us directly to virtual quantum machines, or QVMs, in the cloud. These are directly addressing critical issues like resource utilization, fault isolation, and latency in cloud-based quantum computing. Traditionally, a user might need exclusive access to an entire physical quantum computer for their job because there wasn't a good way to share such a precious, expensive resource, which is incredibly inefficient.
Yeah, one user ties up the whole multi-million-dollar machine. So what's a concrete solution QVMs offer for this problem of resource sharing and efficiency?
Take the HyperQ system, for example. It introduces QVMs that allow multiple virtual machines to execute simultaneously on a single physical quantum computer. It does this by multiplexing them, cleverly sharing resources both in time and space across the physical qubits. A QVM is defined by its specific set of quantum gates and qubits, arranged in a hardware-specific topology that mirrors the physical machine structure, like IBM's I-shaped layout. HyperQ is designed to work seamlessly with existing quantum programs and compilers by cleverly aggregating already compiled programs into composite quantum circuits that can run in parallel on different qubits or time slots of the actual hardware.
So packing multiple jobs onto the hardware smartly.
Exactly. This approach significantly increases the utilization and throughput of expensive quantum hardware, reduces program latency, sometimes by an order of magnitude, and can even improve the fidelity of the results by enabling more efficient error mitigation strategies across the jobs.
And if we connect this back to the bigger picture of our virtual qubits, it sounds like the concept of virtual qubits themselves is a key enabler, maybe even at the lowest physical hardware level, not just in simulation.
You're spot on. The concept of virtual qubits isn't confined to abstract simulations. In trapped ion quantum computers, for instance, researchers are actively exploring encoding multiple logical qubits within a single physical ion.
Multiple logical qubits in one physical ion? How?
By using more of the ion's internal energy levels or states. Using these virtual qubits can allow access to more effective qubits overall and can simplify the required quantum circuits by reducing the number of complex two-qubit interactions needed between separate ions. This, in turn, reduces the reliance on noisy vibrational modes that are normally used to couple ions, leading to potentially lower logical error rates.
Fewer errors, simpler circuits.
Right. For example, studies show that using 2 or 3 virtual qubits per ion can significantly reduce the number of native physical gates needed for certain applications, making the whole system more efficient and potentially more robust against decoherence. So the idea of virtualizing qubits is transforming both the software and the hardware landscapes of quantum computing. It's a powerful abstraction at multiple levels. #tag after.
Today, we've taken a truly deep dive into the audacious vision of the JUMPS blueprint and programmable realities. It's been quite a journey. We've unpacked how virtual quantic blueprints bridge the hardware gap, enabling stage-by-stage qubit manipulation through dynamic digital maps and precise operations, all without the constraints of messy physical hardware.
Yeah, that simulation-first approach is key.
We explored revolutionary frameworks that integrate quantum principles, cutting-edge AI, and even, ancient traditions like Kabbalah and crystallography to redefine computation itself, providing a sort of universal grammar for reality.
We then connected this to the profound theoretical physics of time jumps, understanding how concepts like Aharonov-Vaidman's two-state vector formalism suggest a nonlinear temporal influence.
The backwards in time hints.
Right, and how phenomenological quantum leaps challenge our linear perception of time. And we saw how underlying mathematical structures, like that 126 boundary, are central to this architectural vision, defining the very limits and possibilities of these simulated universes, ensuring their coherence.
This isn't just theoretical, is it? It points to a future where the line between pure physics, computer science, and tangible technology is blurring faster than we realize. You've gained, I think, a unique shortcut to understanding how designers are not just writing code, but literally designing the very structure of computation in a virtual universe, pushing the boundaries of what's possible in a programmable reality.
It's a fundamental redefinition of what it means to create, to simulate, and maybe even to interact with reality itself. It goes deep.
So here's a final provocative thought for you to ponder as we wrap up. If quantum theory suggests time isn't necessarily fixed, that it can perhaps jump or behave in profoundly nonlinear ways at the most fundamental level, and if projects like the JUMPS blueprint are actively exploring how we might literally program reality, or at least simulated realities with entirely different temporal rules, then how might our deeply ingrained perception of linear time, a fixed past, a flowing present, an open future, how might that be fundamentally challenged or even reshaped by these emerging technologies and ideas?
A deep question.
Perhaps the future isn't something we just passively arrive at, but something we might, in some very strange new sense, actively get to shape or even choose, maybe even edit. What do you think?